the elegance of how the core technology, the catalyst works. I don't know if you could tell from earlier, like I started talking very passionately about that. The fundamental science behind how our catalyst works, it was not understood by humanity until about 2016.
Okay.
And so it is elegant, it is beautiful. And if you can really understand like what is happening at the molecular level with our catalyst, it is fundamentally better than what's out there. And I love it.
So welcome to Interviews with Experts, ChemAnalyst flagship series connecting you with top minds in chemical, energy, and innovation. Joining us today is Trevor Best, co-founder, CEO, and board chair of Syzygy Plasmonics, the Houston innovator turning light and renewable power into clean fuels and chemicals via the groundbreaking Regal photoreactor. With over $135 million raised and pilots powering sustainable aviation fuel from biogas, Trevor is redefining green manufacturing. Great to have you, Trevor. Let's dive in.
It is great to be here, and I'm excited to dive into this with you.
So, to kick things off, could you give us the elevator pitch of your journey? How did you end up building a company at the intersection of photonics, catalysis, and clean fuels?
Yeah, so to understand my journey, we need to go back, about 15 years or so to around 2010. I was in 2009, 2010, I was starting my career at Baker Hughes. And through that career in Baker Hughes, I ultimately ended up in the new product development group, developing new products for the energy industry. That was where I met my co-founder, Dr. Suman Kadiwada. Okay. And between the two of us, we worked on more than 100 product development projects. And so we got to see a couple things. We got to see, R&D that worked. We got to see R&D that didn't work. And we got to see, what kinds of things that the market would actually buy and what it took to bring an energy technology to global scale. Fast forwarding a few years, in 2015 and 2016, my co-founder and I were reading, the reports from the International Panel on Climate Change, saying that we had 10 years to do something bold. And we decided that we wanted to go find that bold new technology and apply these learnings. And we saw that we were probably going to have to go strike out on our own and do our own business if we wanted to truly disrupt the industry. Right. So we started a search and we looked at dozens of different scientific papers and ideas and possibilities. And eventually we found the paper for this in late 2016. And we started talking to the professors. My co-founder also went to Rice University. So he used his alumni status to get a call with the professors. And after months and months and months of looking at this, we could not find a reason why it wouldn't work. So we quit our jobs, cashed in our life savings. And in 2017, quit our jobs in 2017, cashed in life savings, launched the company, and raised our first round in 2018. Since then, it's been a honeymoon journey, as you mentioned, 135 million raised, and the tech is working beyond our wildest dreams. It is truly incredible to have watched the journey.
Perfect. That sounds great. So, Trevor, as CEO, how do you balance long-term innovation with the near-term pressure to commercialize in today's fast-moving energy transition?
Yeah, so it's a balance of the final possibility, like how big is the market you're chasing and how exciting is that versus, where the technology development is today. And thankfully, I will say that for most of the company's history, we were in the clean tech boom. So I'm sure everybody remembers, starting in 2020, hydrogen started to become very, very popular. There was tremendous amount of support for clean tech. So it was a great environment to be fundraising in. And our technology, it is a platform technology. It can do many different chemical reactions. We started our focus on hydrogen, which is a huge market, and we were able to show our disruption and raise money continuously. And then now with some of the headwinds facing hydrogen, we have adapted our technology to sustainable aviation fuel, where there is still excitement. And so, to answer your question, you have to be flexible. You have to have a product with more than one value proposition, and you have to be able to adapt it to what the market is excited about and, chasing in that moment.
Understood. So it makes sense. Yeah, you should have product which has more than one value proposition, should have more value proposition out of it. Then only you can commercialize it. Yeah. So, Trevor, when you think about Syzygy 10 years from now, what does winning actually looks like? Would that be technology adoption, market share, or system level impact?
I would say system level impact, and I would really sum that up into like one word, and that is, price. And that is, our single-minded dedication to be lower cost than other pathways. And that's what true success looks like for me. We are, whether I like it or not, I'm talking about hydrogen, I'm talking about, sustainable aviation fuel. These things are ultra commodities. They typically have very low margins and extremely high volumes. And so if you want to have what you called system level impact, if you actually want to make a difference, you have to win on price.
Right.
And so we have a very, very focused mission to be the most affordable sustainable aviation fuel, and eventually 10 years from now get to a point where we are close or at parity with traditional jet fuel.
Okay. So let's talk about technology, for viewers who aren't engineers, maybe chemical engineers. How does Syzygy's light-driven reactor technology fundamentally differ from conventional thermocatalytic processes?
Yeah, so I think the best way to describe this is I'm going to start very small at like the atomic scale, and then I'm going to zoom out and talk a little bit about the reactor, and then I'm going to talk about the plant. So typically, if you have a thermal-driven catalyst, this is a material, if we're talking about like a heterogeneous industrial chemistry that's driving an endothermic reaction, you have these molecules, they will bond together on the surface of this catalyst, and they will pull in energy, heat energy from the environment around them, right, and then get released. This whole process takes a certain amount of time. And sometimes, things like this is called coking, where you get carbon buildup. Sometimes right, things can build up on the surface of the catalyst and slowly deactivate it over time. Syzygy's catalyst is unique for a couple reasons. We are combining a very, powerful, near perfect light harvesting nanoparticle with traditional catalyst nanoparticles. So the light harvesting nanoparticle is catching photons, and it is transferring the energy in those photons, the light, to the catalyst nanoparticles. That process happens about 2 orders of magnitude faster than thermal processes.
Okay.
And quite literally, light just moves faster than heat. And so what's interesting is you can do more chemical reactions, dramatically more chemical reactions in the same amount of time. So our reactors, even though they are small, they have low volume, they can produce a tremendous amount of product. The other thing is I talked about things getting attached to the surface. That light interaction with the catalyst can kick things off the surface. And so the catalyst has natural anti-coking, antioxidation properties that keep it from dying. And this allows us to use difficult feedstocks like biogas. When you zoom out to the reactor, what we're doing is we have a catalyst bed and we sink a light down the middle of it. The light is incredibly efficient. It is about 95% efficient at turning electrons into photons. And because we have embedded the light inside the catalyst, the only exit pathway for the energy is through the catalyst. It is a very efficient design versus a traditional thermal reactor where you have like a burner and a metal tube, and you're trying to get the heat from the flame into the metal tube, it's not very efficient. With us, all of the energy goes into the light, and all of the light goes into the catalyst.
Understood.
And this is how we were able to achieve above 80% energy efficiency in our first field trial at Latte Chemical.
That's great. Yeah.
So finally, for a big system, you're putting in renewable electricity, you're not burning fuel, so no emissions. So basically, very powerful, compact, low-cost, efficient, emission-free chemistry.
Right. So let's talk about NovaSAF. Compared with other SAF pathways like HEFA, ATZ, or FT, where does NovaSAF really shine on cost, scalability, and carbon intensity?
Yeah, so NovaSAF is Syzygy's process for turning biogas from landfills or dairy farms that have anaerobic digesters, etc., ultimately into jet fuel. That process, you take biogas, you put it into our reactor will turn it into syngas, then we put it into a Fischer-Tropsch unit that will upgrade that syngas into liquid Fischer-Tropsch crude, and then finally that Fischer-Tropsch crude is put into a hydrotreater that will upgrade it to on-spec ASTM spec sustainable aviation fuel. Versus other pathways, Syzygy's process, if you locate this in the right areas that have abundant biogas and low cost of power, a great example would be like sugarcane crop residue from Brazil. We can have an overall levelized cost lower than HEFA. And with some additional improvement to our reactor, you talked about what does success look like in the next 10 years? If we can continue our development for the next 10 years like we have for the past 10, we see our technology being able to start getting the overall cost of fuel down into the $3 per gallon range, which is pretty much comparable with jet fuel. So
that's great. Yeah.
That's the price is a differentiator, but it's also very, very good on carbon intensity. And so having done an outside third-party assessment, they determined that the carbon intensity of our process would be about 9 grams per megajoule, which is a 90% reduction versus traditional jet fuel. And also, the third-party assessor has determined our eligibility for ISCC RFNBO in the EU, the United Kingdom's Department for Transportation Power to Liquid program under their RTFO in the UK. And we've also completed our ISCC CORSIA assessment as well. And so these are pre-eligibility studies done by accredited third parties.
Okay.
Yeah, but being able to apply our SAF to the mandate, its very low CI score and its very low cost is quite disruptive.
Right. So NovaSAF 1, this is being positioned as a blueprint project. Correct me if I'm wrong.
That is correct. So located in Durazno, Uruguay, NovaSAF 1 will be the first time that we put all of the pieces together and go from raw biogas to on-spec sustainable aviation fuel and actually apply it to the mandates in the United Kingdom and Europe. And so all of the volume of NovaSAF 1 has been spoken for. A few weeks ago, Syzygy announced a very exciting offtake with Trafigura, where they will be taking the entirety of the output of NovaSAF 1 and trading that into Europe for the mandates. And then the future plants, once NovaSAF 1 is built and operating and we can check the box, yes, it works technically, we have all the logistics worked out, we've got all of the certifications we need, then we will go build in other places like Brazil, Mexico, Dominican Republic, and do much larger much more economic plants as well. And Trafigura has also taken a reserve of those. And so we have them as a partner, not just for the first one, but for the second larger ones too.
Okay. So I had a question on Trafigura. I guess you have answered most of those pointers. So tell me one thing, Trevor. Modular design is a buzzword across clean tech. How does modularity actually helps you scale faster and reduce capex risk?
Yeah, so modularity helps for a couple reasons. One is eliminating a lot of the front-end design work that is needed as you build multiple plants. How you mentioned NovaSAF 1 as a blueprint, instead of having to go design a completely new, type of reactor, like much larger volumetrically or things like that, because of our modular design, whenever we scale up, we do mass manufacturing. So dramatically less engineering needed to deploy projects. Especially once you start getting to like 3 or 4 projects that have been deployed, it is possible to just take those modular designs and, this is what you hear, like quote unquote plug and play into new areas.
Right.
The main way that this reduces capex though is through mass manufacturing. And I like to think the best example we have of this in modern society is the automobile. This is an extremely complex machine with lots of moving parts, but you can buy them for pretty low cost, all things considered, and it's because they make thousands of units at a time. And for our technology, whenever we look out at our market, biogas sources are distributed. So dairy farms, it's not like one giant oil field, they're scattered around. And how we plan to address that is through modular mass manufactured design. For example, there's like 9,000 dairy farms in Germany. And so if we were to do a project there, we wouldn't just go do one, we would get 100 together. And then I go out to my vendors and I order hundreds of components at the same time, and I bring those costs down through mass manufacturing.
Right. Interesting. So let's talk about Trafigura, So long-term offtake agreement with Trafigura turned heads across the industry, So why was this partnership such a pivotal milestone for Syzygy?
So we think it's pivotal not just for us, but for the industry as a whole, for a couple reasons. I'll talk a little bit about us first. So Syzygy, we have been developing a revolutionary new technology for 7-8 years now, and this shows that we are done with that development. We are ready to enter the market. We have something that is commercially interesting, and especially given that this is our first large commercial offtake, we didn't just get it with some random group. Trafigura is one of the world's largest, most accomplished traders, and they don't do things unless if they think they can make money.
Right.
And this really shows that Syzygy has now transitioned from a company that is building a product and has a lot of potential into a company that is starting to execute in the market. And now our disruption is starting to become inevitable. And so I think it's huge for Syzygy, but for the industry, this is really big for a couple reasons. One is I'd mentioned the RFNBO. This stands for Renewable Fuel of Non-Biologic Origin. Prior to this announcement, the only known pathway to get to RFNBO-compliant SAF in Europe was through power to liquids. This is CO2 plus hydrogen. So Syzygy worked with an external third party, Peterson Group, and they are qualified to do these kinds of assessments against the European regulations. And looking into the European regulations, because of the unique way our reactor works, we are actually also able to be eligible for that RFNBO production. And it's pretty much the first time that a non-electrolysis path has checked this box. And given that our cost structure is quite literally half of the power to liquids pathway right now, it is going to be very disruptive. It gives the entire European continent a cost-effective way to meet that RFNBO mandate. And over time, being able to compete with HEFA on cost and given a little more time, potentially being able down to get to jet parity, like this is a huge milestone for the industry as well. This will be remembered, for 15, 20 years from now.
Exciting, very exciting, Trevor. Let's talk about some of the policies and regulations. With SAF mandates emerging across the European Union, UK and beyond, how important are policy frameworks versus pure market demand in driving adoption?
Yeah, so I would say that the policy drives things much more quickly than voluntary demand for new technologies. One of the difficulties in bringing something to market is the early stages, and this is where Syzygy is, and is commonly called a valley of death, where you have to build your first of a kind plant. You might have heard people talk about this as a FOAK plant, FOAK, first of a kind.
Okay.
When you are doing this, you have to build a small one and prove it out. The economics are never good. I talked about fuel as an ultra commodity, and no one will be able to build a first of a kind plant that can compete with traditional technologies that are fully scaled up right out of the gate. And crossing this bridge and getting somebody to believe in your first of a kind plant so you can prove it up and then go build a big one is the bottleneck that kills a lot of new technologies, a lot of companies, etc. And what is so important about how we set up the regulatory frameworks is the governments are what help technologies cross this bridge. Mm-hmm. For example, I talked about the RFNBO mandates. These technologies, without this, would struggle to get their first of a kind plants built because they are more expensive than HEFA today. So I think mandates are a good approach to this, especially since sustainable aviation fuel is a drop-in replacement. And apparently most of the world agrees, because in the past couple months, you've seen like Thailand, United Arab Emirates, South Korea, all start pushing mandate-driven schemes. I've heard of Japan starting to mull subsidies for their mandates. I've heard of China toying around with mandates. And I've even heard of India, discussing mandates a little bit as well. Right. And so, starting off with low percentages, like 1% of fuel, and ratcheting up to 5-10, it pushes the market to adopt new technologies without destroying the economics of the airlines. And this is how companies like mine get traction, get their first plant pulled across the line, and ultimately build huge disruptive facilities.
Great, yeah. So, Trevor, feedstock availability has been a major constraint for SAF. Does biogas meaningfully change the feedstock conversation?
Oh, absolutely. So I'm going to do a thought experiment here, and this I think will start to help people understand how much is out there. I think you and many people probably heard that methane is a very, very potent greenhouse gas, and it is a big problem. And in fact, if you look at all of humanity's carbon footprint, about 10% of all of the emissions that humanity emits are anthropogenic methane emissions. And what does this mean? This means methane from cows and cattle production. This means methane from landfills that comes seeping out. And quite literally, what we are doing is we are capturing a percentage of those emissions and turning it into jet fuel. And if you think about the scope of the problem, like 10% of humanity's emissions, that's a huge, huge volume. And so one way you could look at it a problem, but for me, it's a huge opportunity. That is a lot of feedstock. The International Energy Agency did a biogas and biomethane assessment. And they found a couple things. One is that most of this stuff is stranded. Mm-hmm. So if I talk about Brazil, if they have a big sugarcane plantation and they turn it all into biogas, what do they do with it there? There's no customer there to use it. It's very difficult to get it out. So turning it into a liquid helps unstrand it. So a lot of this resource is stranded. When they looked at the quantity, planet Earth could produce 890, what's called BCME. It stands for billion cubic meter equivalent. And if we turned that into SAF, we could make 500 million tons of SAF a year. And planet Earth only uses like 250 to 300 million tons per year. So we could make
great numbers, yeah.
Yeah, we could potentially make all of the planet's jet fuel need from biogas. Now, listen, not all of it's going to be economic. It's ridiculous to think that planet Earth is going to only use biogas for jet fuel. But when we talk about like feedstock meaningfulness, like, yeah, like almost every city has a landfill, or dairy farms nearby, or food processing, or wastewater treatment, or like there are tremendous amounts of these assets around the world that we aren't using. We're throwing it away into the atmosphere, and we could turn it into jet fuel instead.
Right. My next question is, this is about NovaSAF again. So renewable electricity is a core input for NovaSAF. How sensitive are your project economics to power prices and grid reliability?
Yeah, it's a great question. And there's also another interesting anecdote on why we chose Uruguay for our project in relation to all this. But yes, finding the right electricity at the right cost is critical for us. And so I will say that we are sensitive to the price of power, but we are less sensitive than other power to liquid pathways. So, I talked about that RFNBO. Traditionally, to produce RFNBO compliant SAF, you will need about 4 megawatts, 40 megawatts of power per ton of fuel. We need about 11 megawatts of power per ton of fuel. So it's a pretty dramatic reduction, about 1/4 the amount of power. So I'm less sensitive than some of my competition, but if you go look at like HEFA or something, they need something like, I don't know the number off the top of my head. It's like 3 or 4 megawatts. So they need less than us. But what this ends up meaning is that for prices of power that are around like $50, $60, $70 per megawatt, I can make project economics work. And so I don't need ultra low costs of like, $10 a megawatt, which is unrealistic. But I don't want to go to areas that are extremely expensive at like $200 a megawatt. So we've got to find the right balance, and it does need to be renewable. So we are focusing our work on areas where we can find this, in Canada, like Vancouver, lots of lower cost renewable power there, Brazil, Saudi Arabia, etc. That's where we're planning our first wave of deployments. India, because there is that lower power cost in abundant biogas feedstock.
Right. But Trevor, before evaluating any project locations, there could be a number of parameters which you'd be looking at, not just cost of electricity. It could be policy incentives, clean power access, biogas supply, as you said, and proximity to aviation hubs. Right. So
yeah, exactly. Proximity and logistics is a huge piece.
Right. So let's talk about the competitive landscape. This SAF space is getting crowded with new pathways and startups. How do you think competitive dynamics will evolve over the next 5 years?
So great question. And I think it's good, instead of talking about any individual company, it's good to talk about the different production pathways. And right now you've got in sustainable aviation fuel, you've got HEFA, which is essentially SAF from used cooking oil. You've got alcohol to jet, which is taking corn or some other kind of crop, creating ethanol and then running that through an ethanol to jet fuel process. Mm-hmm. You've got power to liquids, which is green hydrogen plus CO2. And then now you've kind of got Syzygy. We are like a new kind of fourth pathway in all this. So HEFA is by far the dominant player. Pretty much every every large SAF project you hear about today is a HEFA plant making SAF from used cooking oil. From a volume standpoint, they are something like 99% of the volume. The other two pathways, power to liquid and alcohol to jet, while exciting, are still nascent. They still need more development. They need to come to market. And then finally, ours, also very exciting, but also nascent, needs to scale up. My belief is that both power to liquids and alcohol to jet will start to get some projects going. But I think just the economics and things like competing over land for good crop space and things like that are going to make them challenging to do. I think HEFA will continue to grow, and over the next 5 to 10 years, we'll start to hit the feedstock wall on HEFA, where all the lower cost used cooking oil is being accessed, and growing that is going to be feedstock limited. And that's where I think our technology starts to shine. I do think we have a better cost structure than all three of them. And as we start to put together some big projects, I'm from West Texas. I don't know if you've watched any of the like oil field shows like Landman or anything like that, but there's a term that we use called a land grab. And basically it comes from back in the day. If you find oil, everybody rushes in to try and get spots.
Right.
Yep. I think for our pathway, like biogas, electrified biogas to SAF, I think that we are at the beginning of a land grab. I've already found enough to make about 1 to 2 million tons of SAF per year, which is a tremendous amount, and I'm still just scratching the surface. So over the next 5 to 10 years, I think it's going to be a biogas to SAF play. I think there's going to be a land grab, and I think that towards the end of that 10 years, they'll even start to, even HEFA will be challenged against the price structure that biogas to SAF can offer.
That's interesting, yeah. So now let's talk beyond aviation. Looking past SAF, where else do you see Syzygy technology creating value? Would that be clean hydrogen, e-methanol, chemicals, or industrial heat?
So industrial heat, that's probably going to be somebody else's play. But the rest of them, simply like, yes, absolutely, we will create value in all those sectors. So we talked a little bit at the beginning about Syzygy's technology. And the core of our technology is the ability to turn a traditional catalyst into a high-performing photocatalyst.
Okay.
All these benefits that I am talking about, sustainable aviation fuel and how we are able to be more affordable and how we're able to access difficult to use feedstocks and use less power and all of these things, it all comes down to that catalyst and how special it is. And so far, we need a beachhead market. I need to go start making big systems out in the world, and SAF is a perfect market for that. But we have also used our technology to make hydrogen from multiple different pathways. We have synthesized ammonia, which is a base for fertilizer. We have a project right now for butadiene, which is synthetic rubber. We have made ethylene, which is a base for plastics.
Great.
And we have done dozens of other chemical reactions. And so start with SAF, but over the coming decades, we fully plan to try and push our technology into every corner of the chemical and fuels infrastructure, because we can make a reactor that is smaller, lower cost, produces more product, and runs more efficiently than traditional tech. And it helps us a lot for SAF, but it will help us a lot in other areas as well as we push into those. So pardon our ambition, but we're here to try and change the world, and we're going to go for it.
Yeah, that's great. Yeah. Now let's look at the bigger picture. So as we move toward a low carbon fuels economy across aviation, shipping, and chemicals, how does Syzygy decide where to place its bets?
So I'm watching the market and trying to anticipate like what is going to happen in the future. And yeah, I'll just talk about like what we've done in the past and why we made those decisions, and then I'll make some interesting points for the future. So in the past, going back to 2017, 2018, we saw that if the world wanted to fight climate change in the way that it was saying it was at that time, hydrogen would be necessary. There was no way that you would be able to make huge impact on global emission amounts without hydrogen. And so we knew that hydrogen, what something was going to happen there. That's why we started our work on hydrogen in the very beginning. Around 2021, we saw that there was a break, and we started seeing a lot of people push for $1 per kilogram green hydrogen. And just knowing the techno-economics behind that, we knew that that was never going to happen. It does not take much work to understand why $1 per kilogram green hydrogen won't happen. You need electricity prices at like $10 a megawatt or less. And you basically need free electricity, and building a business on the assumption that you're going to get free electricity is, yeah. So we started to say, okay, hydrogen is a bubble; it will pop.
Right.
So what do we pursue next? And that was when we started to work on sustainable aviation fuel. We saw that unlike hydrogen, you did not need to replace the production process and the receiving process. Because it's a drop-in replacement, you only had to change the production process, so that made adoption easier. And we also saw that the mandates and incentives around sustainable fuel were much stronger than those around hydrogen.
Okay.
So ultimately, after looking at a lot of things, like methanol didn't have it, ethylene didn't have it, sustainable aviation fuel had this network of drop-in replacement, incentives and mandates across the world, and some level of voluntary demand. So it was the right choice. Now I'm looking, into the future, and I'm seeing trends. We are seeing that there is, an anti-globalization trend right now. Nations are becoming more isolationist, and we're looking at what does that mean for the world? And so if global import-export drives prices up, there are certain, not the super commodities like fuel or hydrogen, but there's certain intermediate molecules like naphtha and what you can do with that could have interesting applications, around the world. So we're starting to do some early stage research into hey, what can you turn naphtha into? Because if import-export starts to break down, then you get some of these lower value molecules that get stranded, and there could be some big opportunities to turn them into higher value molecules that would traditionally be imported or exported. It's quite similar to what's happening in critical minerals right now. How do we how do we help nations reshore production capability for middle, intermediate chemical precursors and things like this? And it's a very interesting thing because these usually only make sense if you build mega plants, but because we have a smaller modular tech, we could help countries make them closer to the point of consumption. And this could have defense implications. It could have lots of things. So looking at that, and I think that's going to be a mega trend over the next 5 to 10 years. And the other one is if planet Earth continues to look at CO2 utilization, we need the pendulum to swing back towards clean tech a little bit from where it is right now. But I have held for many years that methanol, I think, is the most interesting molecule out there. It is a fuel, it is a chemical precursor, it is a carbon carrier. So I think that there's a lot of potential around methanol that the world will realize. But we need more clean tech. We need the pendulum to start coming back the other way. I think if methanol is going to get exciting.
Right. So finally, on a personal note, what excites you most right now? The technology breakthroughs, the commercial traction, or the chance to reshape how fuels are made?
Me personally, I'm excited by all of it. It's my job to be happy and excited about these things. But if I had to pick a single one, the elegance of how the core technology, the catalyst works. I don't know if you could tell from earlier, like I started talking very passionately about that. The fundamental science behind how our catalyst works, it was not understood by humanity until about 2016. Okay. And so it is elegant, it is beautiful, and if you can really understand like what is happening at the molecular level with our catalyst, it is fundamentally better than what's out there, and I love it. Reshaping the future of fuels, disrupting industry, getting commercial traction, it's all because of those little nanoparticles, and like I love them, and I think that fuels are just the beginning, and it's because of that core science. That's what gets me out of bed in the morning. I've got to get this out there.
That's very exciting, Trevor. So, Trevor, those were all the questions I wanted to ask. And all the best for the future.
Okay. Thank you so much, Rahul. It was great talking, and looking forward to staying in touch.
Sure, Trevor.